Welcome to Course 4, Module 4, Chapter 10, which focuses on data traceability and digital passports as practical foundations for circular economy strategies. The central idea is simple. Circularity cannot be managed if materials, components, and products disappear from view after sale, use, or disposal. This chapter explains how organizations can make those flows visible through product-level data, lifecycle information systems, digital product passports, and blockchain-based records. We will look at why linear supply chains create information black holes, what data architectures are needed to track materials across multiple life cycles, and how emerging regulations are turning traceability into a compliance requirement. Today we start with the idea that product design is the foundation of circular supply chains, because it determines which recovery options are technically and economically possible. We then discuss the often quoted 80% rule and explain why it should be treated as a strong signal rather than a universal law. After that, we turn to engineering principles, especially modularity and design for disassembly. The middle sections connect those principles to material choices, organizational collaboration, and design briefs. Finally, we apply the concepts to Renault, Tata Steel, and Wonpanet. The goal is not only to understand circularity, but to see how it becomes operational. Use the sequence to show how each topic builds toward integrated closed-loop execution. This section introduces the chapter's core argument. Circular economy strategies require reliable data about products, materials, use, and recovery options. Traceability technologies help close material loops, but they also create organizational and governance challenges. The first major takeaway is that traceability functions like the operating system of circularity. In a linear economy, companies often lose sight of products once they move downstream, and they rarely have reliable information when those products return as waste or secondary materials. Circular strategies require the opposite. Firms need continuous visibility into location, ownership, condition, composition, and life cycle history. This is what allows reverse logistics to work, enables safe recycling, supports compliance, and makes circular business models credible. The chapter connects this requirement to digital tools such as IoT sensors, blockchain ledgers, digital twins, and digital product passports. Each tool contributes differently, but together they create the information infrastructure needed to move from isolated transactions toward managed circular material flows. The sector reviews in the source document show that traceability is not a niche concern. In textiles, researchers emphasize digital garment identities and the use of blockchain or IoT to follow products through complex value chains. In plastics, studies point to physical markers, certification systems, blockchain, and digital product passports as ways to identify material streams and improve recycling quality. Reusable packaging research also argues for digital passports and mandatory reporting because reuse systems need reliable records of circulation, returns, and losses. These examples differ by industry, but they point to the same underlying pattern. Circularity depends on linking material flows with information flows across many organizations. Without that connection, reuse, recycling, and accountability remain difficult to scale. This pattern reappears throughout the chapter. Beyond individual sectors, broader circular economy research describes the digital backbone required for circular strategies. Smart circular economy frameworks combine IoT, big data, analytics, and information systems to track product and material flows more intelligently. The purpose is not simply to collect more data, but to turn data into decisions about resource management, recovery opportunities, and circular interventions. Information systems research is especially important here because circularity often requires cooperation beyond one firm's boundaries. Data must move between suppliers, manufacturers, users, recyclers, regulators, and service providers. Distributed ledger technologies can add trust where multiple actors share records. The overall message is that circular economy implementation is both a technical and an organizational information challenge. Effective circular systems therefore depend on shared digital foundations. This section explains why circular supply chains need end-to-end visibility. When product and material information disappears, organizations cannot plan reverse logistics, verify claims, recover value, or manage circular flows effectively. This slide identifies 4 recurring places where linear supply chains go dark. First, provenance may be unclear, meaning firms do not know the origin or processing conditions of materials. That creates ethical, legal, quality, and safety risks. Second, data may be trapped in organizational silos, so information is delayed, incomplete, or unavailable to other actors. Third, end-of-life flows are often opaque because products disappear into waste systems, informal collection networks, or mixed material streams. Fourth, some sectors are especially fragmented. Plastics and textiles, for example, face contamination, composite materials, and many small actors. The consequence is direct. Without visibility, firms cannot locate materials, assess their quality, organize recovery, or circulate them profitably. These gaps explain why digital traceability becomes strategically important. In sectors such as cobalt and pharmaceuticals, the issue is often provenance and compliance risk, so blockchain-based traceability can help create tamper-resistant records of origin and handling. In textiles and clothing, weak product tracking and origin authenticity can be addressed through digital identities, IoT tags, and blockchain records. In plastics, the challenge is chain-wide transparency, which requires holistic mapping and collaboration among many stakeholders. For reverse logistics, conceptual circular supply chain frameworks help organizations design the system conditions for return flows. The key point is that technology should not be applied generically. It should be matched to the precise place where material and information flows break down. That matching determines whether visibility actually improves. End-to-end visibility matters because it turns circular ambition into operational control. To close loops, companies need to know where products are, who controls them, and what condition they are in. To reduce leakage, they need to identify bottlenecks before valuable items become waste. To build circular business models, they need better data about resources, costs, recovery processes, and benefits. And to create trust, they need reliable evidence for compliance, incentives, certifications, and sustainability claims. The chapter's practical requirement is continuous knowledge of material flows, actors, and physical condition. Circular supply chains cannot rely only on snapshots, averages, or annual reporting. They need real-time or regularly updated traceability systems that support day-to-day decisions. This is the operational meaning of circular visibility. This section shifts from visibility to architecture. Circular systems need data models that follow products across design, use, maintenance, recovery, and recycling, creating a digital thread for practical circular decisions. A circular architecture must integrate beginning of life, middle of life, and end of life information. Beginning of life data includes design specifications, component structures, materials, manufacturing processes, and supplier information. Middle of life data covers use, maintenance, upgrades, repairs, condition, and remaining performance. End of life data includes collection, sorting, disassembly, recycling, disposal, and potential recovery pathways. When these phases are disconnected, circular decisions become guesswork. When they are connected through persistent identifiers and linked records, the result is a digital thread that can support design for circularity, product life extension, remanufacturing, and recycling. Digital product passports can serve as a practical interface for this architecture because they connect product records across organizations and lifecycle phases. This creates one shared basis for circular decisions. This connection makes the lifecycle model operational in practice. There are several types of product knowledge that circular systems must capture. First, the system must understand product structure, components, assemblies, modularity, repair logic, and disassembly pathways. Second, it must record material composition, including properties, hazardous substances, recycling compatibility, and opportunities for industrial symbiosis. Third, it must track usage and condition, such as maintenance history, wear, upgrades, and remaining useful life. Fourth, it needs persistent identifiers that connect the physical item to its digital records. These data entities support practical decisions. A product may be reused, upgraded, remanufactured, or recycled depending on its condition and material evidence. Without this evidence, valuable circular options can be missed. The architecture therefore turns product knowledge into recovery choices. In real practice, this slide highlights the integration layer, which is essential because circular data is usually spread across many systems. Product lifecycle management systems hold design and component information. Supply chain management systems track movement and actors. Enterprise resource planning systems contain procurement, production, and transaction data. IoT devices provide condition and usage signals. Life cycle assessment tools and material databases add sustainability and composition information. For circularity, these sources cannot remain isolated. They need standard identifiers, shared schemas, open interfaces, and cross-firm traceability so data can be reused across strategies. The integration layer is therefore what turns scattered enterprise data into a connected pipeline for reuse, remanufacturing, recycling, compliance, and circular decision-making. It is the backbone of data interoperability. At scale, the architecture stack shows how a usable circular data system is built in layers. At the base, data capture comes from sensors, enterprise systems, certification records, public material databases, and manual inputs. Above that, the integration layer connects identifiers, schemas, interfaces, and pipelines. The trust and access layer manages permissions, privacy, immutability, and data sovereignty. The analytics layer then uses lifecycle data for big data analysis, artificial intelligence, and scenario modeling. Finally, the decision layer supports practical choices such as refurbishment, recycling, lifetime extension, and remanufacturing planning. The major design tension is clear. Circularity requires broad data sharing, but firms also need confidentiality, intellectual property protection, and controlled access. Good architecture must balance collaboration with protection across complex value chains. This section introduces digital product passports. A DPP links a physical product to a persistent digital record, allowing manufacturers, users, recyclers, auditors, and regulators to work from shared product evidence. A digital product passport makes product-level data electronically accessible through a product-specific record. The basic formula is a data set, a data carrier, and a persistent identifier. The data carrier could be a QR code, tag, or similar mechanism that connects the physical product to its digital record. The record can include origin, material composition, repairability, recycling options, sustainability data, and process information collected along the value chain. From an information systems perspective, this is powerful because the passport crosses organizational boundaries. It allows data produced by one actor to support decisions made by another. For circular economy strategies, that means better repair, safer recycling, more credible claims, and improved coordination. In short, the DPP makes product evidence portable. Clearly, the chapter groups digital product passport architecture into 4 structural elements. The first is identification, where unique product identifiers or GS1 codes connect physical items to digital records. The second is the data model, which defines what information is collected and whether the structure is lean, layered, or more comprehensive. The third is infrastructure, such as cloud platforms, databases, consortium systems, or decentralized architectures. The fourth is access and permissions, which determine what information is open, restricted, private, or shared with selected stakeholders. These choices strongly influence whether a DPP is usable and trusted. A passport must be detailed enough to support circular decisions, but controlled enough to respect privacy, competition, and data sovereignty. Design choices therefore shape practical adoption. The plastics case makes the idea of a digital product passport more concrete. In the example, recycled bottle caps were turned into frisbees, and the process used a GS1-based one-layer passport to track 2,192 frisbees and 486.7 kilograms of recycled material. The case shows that DPPs can support transparent records by combining agreed datasets, tagging methods, and both manual and automatic data capture. It also reveals an important governance lesson. High transparency improves accountability and makes the circular story easier to verify. But a one-layer structure is limited when sensitive information is involved. More advanced DPP designs may therefore need separate open and restricted data layers. The pilot demonstrates feasibility while exposing governance limits. In practical operational settings. This slide summarizes one of the central design trade-offs in digital product passports. Openness versus sovereignty. Open data layers support flexibility, transparency, accountability, and easier access for recyclers, consumers, auditors, or regulators. Restricted data layers protect privacy, intellectual property, commercial confidentiality, and stakeholder trust. The challenge is that both are necessary. Too much openness may discourage participation, while too much restriction may make the passport useless for circular decisions. Decentralized DPP architectures try to balance this tension through identity management, traceability functions, and access permissions. The broader lesson is that DPPs are not only technical tools. They are governance arrangements for sharing product data responsibly across value chains. Trust depends on that balance for all actors across the wider system. This section shows how DPPs are becoming compliance infrastructure. Regulation, especially the EU ESPR, requires standardized lifecycle product information, so organizations must prepare data, systems, governance, and processes. The ESPR changes digital product passports from a nice-to-have tool into compliance infrastructure. Its purpose is to make product information standardized, comparable, and reliable across the lifecycle. That includes data about material composition, components, substances of concern, repairability, and end-of-life pathways. For organizations, the readiness challenge is not only technical. They must align DPP data with existing labels, reporting systems, product regulations, and internal information systems. If this is handled poorly, companies may duplicate administrative work or create inconsistent records. If it is handled well, DPPs can become a single source of structured product information that supports circular design, customer transparency, regulatory audits, and sustainability claims. Compliance can therefore also create strategic data value when implemented with strong organizational governance. A practical readiness checklist includes 4 capability themes. The first is high-quality data scope. Organizations need lifecycle information that is standardized, accurate, and machine-readable. The second is IT and data management. Systems must structure, connect, and share product data across firm boundaries. The third is governance and compliance. DPP processes must align with existing labels, regulations, reporting routines, and responsibilities. The fourth is trust and interoperability. Stakeholders need secure, privacy-preserving ways to exchange data. The maturity model perspective is important because it shows that technology and organizational processes must develop together. A regulation can create pressure, but operational capability depends on data quality, roles, workflows, and shared standards. These capabilities should mature before reporting deadlines arrive. Across the whole organization, regulatory readiness differs by sector because each circular system has different operating conditions. In reusable packaging, digital passports and reporting systems can support auditing of reuse rates, tracking of returns, health and safety recalls, taxation, and incentive schemes. The challenge is to make many repeated movements visible and auditable. In low-carbon hydrogen, the focus is different. Stakeholders need verifiable carbon footprint data, tamper-proof processing records, privacy-preserving sharing, and interoperability for global markets. Despite these differences, the common thread is clear. Digital product passports become the data infrastructure behind credible claims, auditing, and incentives. They translate regulatory expectations into concrete design requirements for information systems. Sector context determines the exact implementation path, and directly links policy goals to daily operational data practices. This section gives a balanced view of blockchain for secondary materials. The technology promises trusted traceability and verification, but real-world evidence for scaled secondary material systems remains limited. The evidence gap is important for understanding blockchain realistically. The literature contains many conceptual models that describe how blockchain could improve circular supply chains. Some simulations assume better carbon tracking or more effective recycling when ledger-based information is available. Other studies examine managerial perceptions and suggest that firms see value for green manufacturing, waste valorization, and recycling. Yet scaled empirical proof for secondary materials remains limited. Many operational examples still focus on primary chains, where materials move in a more linear direction. The chapter's conclusion is not that blockchain is irrelevant. Instead, it argues that operational architecture exists, but stronger evidence is needed before claims about secondary material sustainability can be considered fully proven. The field is promising, but still maturing. The lensing fiber to garment case illustrates both the promise and the limits of blockchain traceability. On the positive side, blockchain can help authenticate sustainable fibers in final garments, share upstream certifications with brands, and create one immutable source of supplier practice data. This improves transparency and gives downstream actors better evidence about the origin and handling of materials. However, the chapter also stresses that blockchain cannot replace physical verification. A ledger only protects the integrity of recorded data after it has been entered. If the original input is wrong, incomplete, or fraudulent, the technology cannot automatically correct it. Real-world audits, certification, and governance remain essential complements to digital records. Digital trust still begins with reliable physical evidence. Throughout the value chain. This section explains blockchain's role in chain of custody. Distributed ledgers can support provenance, recycled content verification, and audit records, but they must be combined with governance, standards, and reliable physical verification. The chapter identifies three major roles for blockchain in material chain of custody. First, it can support immutable provenance by recording due diligence evidence for conflict-free and ethically sourced materials. Second, it can help verify recycled content through tokenization, lifecycle tracking, and records that support trusted secondary material markets. Third, it can improve audit and compliance processes by creating transparent, shareable records for regulators, certifiers, and business partners. However, the socio-technical caution is essential. Blockchain systems must be paired with inclusive governance, standardized protocols, fair participation rules, and reliable verification. Otherwise, the technology may create a digital record without solving deeper problems of trust, access, or accountability. The ledger is only one part of assurance. when used for credible circular assurance. This section connects the theory to practice through global cases. Automotive batteries, Indian plastics recycling, and Thai organic agriculture show how digital traceability can close information gaps and support credible circularity. The first case is Volvo Cars and Circular in Europe, where battery passports use blockchain-supported traceability to map cobalt and lithium from mine to vehicle. This supports due diligence, conflict-free sourcing, and readiness for battery regulation. The second case is Banyan Nation in India, where dashboards and IoT smart scales help formalize informal waste collection and verify the quality of secondary plastics. This connects social inclusion with material traceability. The third case is the quintuple helix blockchain pilot in Thailand, where blockchain and IoT sensors track organic compliance and carbon-related data for export credibility. Across all three cases, digital visibility turns scattered or informal information into evidence that can support trust, auditing, circular markets, and sustainability claims. And strategic priorities. The conclusion brings the chapter together around three messages. First, design choices set the options. Modularity, design for disassembly, and early life cycle assessment determine whether repair, reuse, remanufacturing, and recycling remain feasible. Second, material simplicity sets quality. Monomaterials and homogeneous streams reduce sorting costs, property loss, and uncertainty in closed-loop recovery. Third, integrated teams set execution. Reverse logistics, procurement, suppliers, operations, and human resource incentives must enter the design brief from the start. The final takeaway is that closed-loop systems are not recovered only at the end of life. They are designed, procured, operated, and improved as one connected system from the beginning. This closes the argument by linking design feasibility, material quality, organizational execution, system resilience, and long-term recovery performance. Thank you for your attention. Next, we continue with Module 4, Chapter 11.